Hi, welcome back to another video for IB Environmental Systems and Societies. Today we're going to cover topic 6.1, an introduction to the atmosphere. The first big idea about the atmosphere is that it is a dynamic and constantly changing system, and that system is essential to life on Earth. The diagram you see on the screen is a nice systems diagram that shows all of the incoming solar radiation from our sun, and it also shows the outputs of energy from our planet via the atmosphere. Right? You see in this diagram, we have a bunch of transfers or movement of energy. We also have transformations of energy when incoming sunlight is absorbed by either clouds directly absorbed by the atmospheric gases or the surface of the planet itself. If you don't remember the stuff about systems and models, go back to topics 1.2 and 1.3 and review them. Right? I want to clarify something that is frequently confusing for students, and that is the difference between the greenhouse effect and global warming. The greenhouse effect is absolutely essential for life on our planet. Without the greenhouse effect, there's no life on Earth. It's a cold, dead planet like we've seen in other star systems and in other places in our own solar system. The greenhouse effect is good. It makes it so that our planet is habitable. Climate change is human-induced positive feedback of the greenhouse effect, so that the greenhouse effect begins to build upon itself and establish a new equilibrium of higher and higher temperatures in the atmosphere. The next big idea about the atmosphere is that the atmosphere is really responsible for the development of the terrestrial biomes that we see across the surface of our planet. In this diagram you see on the screen, you should recognize it from our experiences in topic 2.4. It's called a Whittaker biome diagram, and it shows how precipitation and temperature in the atmosphere are the predominant influences on the types of biomes we find here on Earth. Okay, the structure of the atmosphere. The diagram you see here shows the troposphere, tropopause, the stratosphere, stratopause, mesosphere, mesopause, and thermosphere. In all my years of teaching ESS, I've never seen detailed questions about the structure of the atmosphere unless they're accompanied with a diagram like this. The two parts of the atmosphere, the two layers of the atmosphere that you really need to concern yourself with are the troposphere, which is right here on the surface of the planet where we live, and the stratosphere, which is the next layer up, because that is where the ozone layer is found. Those are the two layers you really need to concern yourself with. Right? We've said that the atmosphere is dynamic. That means it's constantly changing. And in this diagram, or this graph, you can see that we have carbon dioxide, temperature, and sea levels mapped out, and that they fluctuate over time. Here they fluctuated, we're showing how they've changed over the last 400,000 years. And you'll notice that changes in carbon dioxide seem to have a strong correlation with changes in both temperature and sea level. Temperature, sea level involved in the hydrologic cycle influences the amount of moisture in the atmosphere. That's precipitation. This is how the atmosphere influences global climate and creates those terrestrial biomes. When I first put this slide together several years ago, CO2 levels in the atmosphere were about 385 parts per million. When I just looked the other day in September 2023, we were sitting at around 416 to 418 parts per million. So even in just a few short years, we are still adding more and more carbon dioxide to our atmosphere. In ESS, you don't generally need to memorize a lot of numbers, but these might be worth it. They're relatively simple. You should remember that about 78% of Earth's atmosphere is made up of nitrogen gas. That's N2, it's diatomic nitrogen. And that 21% is the diatomic oxygen gas that we rely on to breathe. The remaining 1% of our atmosphere is made up of what we call trace gases. And in trace gases, you'll find water vapor, which is where the entire hydrological cycle runs through, as well as the carbon dioxide and other greenhouse gases. So those make up a tiny fraction of our atmosphere and yet have really massive impacts on life on the surface of the planet. What people do on Earth directly impacts the atmosphere that we live within. The single biggest example of that is probably our release of these very large storages of carbon through combustion into the atmosphere. So we're changing the concentration of carbon dioxide. If you remember, it's a tiny little fraction, 0.03% of the atmosphere. And here in these geological reservoirs where we have fossil fuels, we've got 300 million years of carbon that humanity has been releasing in just the past couple of hundred years. So the rate of that transfer of carbon from inside the planet into the atmosphere is radically changed in the last 200 years. Here you go again. The two layers of the atmosphere you need to familiarize yourself with the most are the troposphere and the stratosphere. The troposphere is where the vast majority of life processes on our planet happens. That's where our weather happens. That's where people live. That's where our industries are. That's where most of our transportation happens, right? The stratosphere is really significantly important because specifically of this ozone layer that protects us from the sun's ultraviolet radiation. And we're going to look at that ozone layer in more depth in just a little bit. Clouds are not just pretty things that people like to look at when they're daydreaming, right? They form in the troposphere and they play a really important role in regulating the temperature of our planet through a process called the albedo effect. Albedo is simply a measure of the reflectivity of a surface. Light-colored surfaces, white surfaces like the shirt that I'm wearing, reflect a lot of light. Darker colors reflect very little light, and instead they absorb it. And when darker surfaces absorb light energy, they warm up. And that plays an important role in the way that Earth's climate is regulated, which we'll explore when we've talked about positive feedback mechanisms, in particular around the melting of Arctic ice over the oceans. So high albedo, high reflectivity, low absorption of solar energy, that keeps things cool. Low albedo is low reflectivity, high absorption, and warms things up. So here you go, some data to show this. You can see the reflectivity of different surfaces. Dry snow, wet snow, bare ice, these are all relatively light colors. They reflect high percentages of light. When you get down here, and I'm sorry that this is kind of behind my picture here, you have darker surfaces such as exposed water. They absorb a lot more light, and you see the reflectivity is significantly lower there. Right? The greenhouse effect, you should be able to outline how it works. Right? Incoming solar radiation, some of it passes through the atmosphere to reach the surface of the planet. What reaches the surface of the planet may either be reflected by the surface of the planet, that's the albedo effect we were just discussing, or it may be absorbed, right? And it may be absorbed by water over the oceans, which cover 70-something% of the surface of the Earth, or by the land. When the surface of the planet absorbs incoming solar radiation and the atoms and the molecules that make up the planet warm up, they begin to vibrate, and they give off or they expel some of that stored energy. They expel it as infrared radiation. Some of that infrared radiation, which is long wavelength, it passes through the atmosphere and into outer space where it's lost to our planet. But some of it is trapped within the atmosphere. And in particular, it's trapped by carbon dioxide, water vapor, and methane, which are three really important greenhouse gases to know about. So you may be asked to discuss the role of the albedo effect from clouds in regulating Earth's temperature. Right? So in this mechanism right here, right, you see the incoming solar radiation strikes the light-colored snow and ice, and most of it is reflected. Right? So that keeps temperatures relatively cool. But as temperatures warm, right, more of this water absorbs light, warms up, and melts more of the ice, which exposes more of the water to absorb incoming solar radiation. Right? So there's a feedback mechanism involved in the albedo effect. This is of the surface. But if you look at the clouds here, this is a bit different. Right? Clouds also reflect sunlight. If you have a lot of clouds, you have quite a bit of albedo, a lot of sunlight is reflected. That tends to cool things off. With cooler temperatures, there's less evaporation, and with less evaporation, there's less water in the atmosphere to form clouds. So the number of clouds decreases, which means more sunlight strikes the surface of the planet, warming the planet, driving a greater amount of evaporation, which means more water in the atmosphere, which means more clouds. And more clouds reflects more sunlight, which cools the planet. So the clouds have this really important role as a negative feedback mechanism to help regulate over long periods of time the climate of our planet. Right? Outline the role of the greenhouse effect in regulating Earth's temperature. If there weren't an atmosphere on our planet would be much colder than it is today. Right? And again, I'm going to remind you, don't confuse the greenhouse effect with global warming or climate change. They are related, but distinctly different. Right? Later on in topic 6, we're going to learn about ozone depleting substances in the stratosphere. We're going to learn about photochemical smog in urban areas. We're going to learn about acid deposition. And all of those are examples of non-point source pollution. And all of them involve pollutants that traverse political boundaries and may not affect people in the places where the pollutants are released into the environment. So we're going to loop back all the way back to topic 1.5, humans and pollution, where we learned about different types of pollutants and established those 3 tiers of pollution management strategies. So if you see a question about pollution management strategies in relation to Earth's atmosphere, come back to these international mindedness ideas here, and that should help you formulate your responses. Welcome. This is a quick video from the IB Environmental Systems and Societies course, topic 6, Atmospheric Systems. Today's video will focus on the formation and dynamic equilibrium of stratospheric ozone and how it protects life on Earth. The big idea here is that ozone found in the stratosphere protects living organisms on the surface of the planet from the sun's ultraviolet radiation. In this image here, you can see that ozone found in the stratosphere, in the lower stratosphere, is called stratospheric ozone, and that is beneficial because it absorbs this ultraviolet radiation. Well, you can see that there's very little of the UVC or the UVB penetrating that layer. Stratospheric ozone is good for living organisms and our planet because it filters out this ultraviolet B and ultraviolet C. Stratospheric ozone, or ozone found in the stratosphere, is different from tropospheric ozone, or surface level ozone, because that ozone found at the surface of the planet contributes to smog and urban air pollution. So even though the molecule is the same, it's O3 in both places, where it is found, it determines whether it has a positive or negative impact on people and the planet. Ozone is a molecule made of 3 oxygen atoms. Most of the ozone in the stratosphere protects us from harmful ultraviolet radiation from the sun. Right? It's formed because it begins with diatomic oxygen molecules, 2 atoms, O2, and they are split by hard ultraviolet rays into 2 individual oxygen atoms. Those individual oxygen atoms then combine with other diatomic oxygen molecules to form ozone, or O3. Right? This process is called photolysis. So they're photolized. Right? O3 is less stable than O2. And so it will, over time, break down or decompose and reform O2 molecules. So 2 ozones will break down and form 3 diatomic oxygens. That formation and destruction and reformation happens over and over and over again, trillions of times every day in Earth's stratosphere in a dynamic equilibrium. That means the overall concentration of ozone in the stratosphere remains constant, even though individual diatomic oxygen and ozone molecules are constantly being formed and broken apart and reformed and broken apart again. The rate of ozone formation is equal to the rate of ozone destruction. All right, welcome back to another video about International Baccalaureate's Environmental Systems and Societies course. This video is about topic 6.3, photochemical smog. The first big idea in topic 6.3 is that fossil fuels produce primary pollutants, and that those primary pollutants, the first pollutants produced, create secondary pollutants, and that those secondary pollutants are the things that actually create smog. For ESS, you really should know what your primary pollutants are, and the main ones you need to be aware of are sulfur dioxide and oxides of nitrogen. If you'll notice here, there's a little X next to the O. That's because nitrogen and oxygen can combine in several different forms. Sometimes it's nitrogen monoxide, sometimes it's nitrogen dioxide, it might be dinitrogen trioxide. All you need to do is call them oxides of nitrogen, right? Your sulfur dioxides come predominantly from the production of electricity at power plants through the burning of coal, because a lot of coal has sulfur in it. If you'll see, only about 5% of it comes from vehicular traffic. You don't need to know these percentages. You just need to know that the primary source, or the main source, of sulfur dioxide as a primary pollutant is the burning of coal to produce electricity. On the other hand, these different oxides of nitrogen come predominantly from vehicular traffic. Right? Some of it comes from burning coal, but most of it comes from cars and trucks on the road. All right? Your primary pollutants, the sulfur dioxide and the oxides of nitrogen, right, themselves are not what causes the smog. Right? What causes the smog is when those primary pollutants, the oxides of nitrogen and sulfur, they undergo chemical reactions in the atmosphere, which then produces ozone in the troposphere. That's ground level ozone. And that ground level ozone is the main component of photochemical smog. Here's a little animated chemical reaction to show you how it works. Right? Your primary pollutants here, right, interact with hydroxides in the atmosphere and the nitrogen oxides, right? And because of that, what they do is they actually release individual oxygen atoms that bond with free diatomic oxygen in the atmosphere to create ozone. And the ozone that is in the troposphere at ground level, that's the bad ozone. Remember, ozone is ozone. It's still O3. Ozone in the stratosphere, where we have the ozone layer, is good ozone because it filters out that ultraviolet radiation. Whereas ozone in the troposphere down here at the surface of the planet is a bad ozone because of the way it reacts with living organisms and different materials. Okay, let's take a look at some of those impacts. Right? The big idea, of course, is that smog has significant impacts on people and living systems. This is, after all, an environmental systems and societies class. Right? So we've been able to study the economic impacts of photochemical smog, right? In California, back in, I don't know, about 10 years ago or so, they estimated at about $500 million US annually in healthcare costs associated with smog. Right? Why smog is harmful? It burns your eyes. It's like constantly living in a cloud of cigarette smoke. Right? It aggravates the alveoli and the lungs. It stresses out your lungs, produces shortness of breath, which makes your body work harder, which can lead to wear and tear on your cardiovascular system over time, leading to an increase in heart attacks. Right? There's a lot of health effects. So those are human health effects that you should know. There are also direct impacts on other organisms, particularly producers. Right? You can see this little brown area or damaged area of this leaf. This is ozone damage because ozone interacts with the outer layers of these plants. And wherever you see this brown, this plant is no longer able to photosynthesize. So it's producing less biomass or energy to feed into the ecosystem. And these brown areas are also areas of weakness, and they allow different disease pathogens to enter the plant and can make the plant sick or susceptible to disease over time. Right? So again, impacts of ozone: irritates eyes, causes respiratory illnesses. Right? You should know that it is a complex mixture of several different pollutants. You should always refer to ground level ozone as tropospheric ozone, or you can call it ground level ozone. You just need to be able to distinguish it, make it clear when you're writing on your ESS exam that you distinguish ozone at the ground from ozone in the stratosphere, where the ozone layer is. In ESS, you don't need to know the complexities of these chemical reactions. What you need to know is that your oxides of nitrogen and your oxides of sulfur undergo a series of chemical reactions in the atmosphere to produce ground level ozone, and that is the primary ingredient to smog in cities. Right? Here you've got Warsaw, Poland. This is Delhi in India, and frankly, this picture is not as bad as it frequently is. This is what Los Angeles always looked like when I was a kid growing up in the United States. And this is Santiago, Chile. And I want you to look at this picture carefully. Right here in the middle, you have this dense layer of really thick, nasty brown photochemical smog. This is what it looks like. And I want you to look at the topography here, the shape of the land. You've got all these mountains in the background, right? Those mountains play a critical role in Santiago's smog problem because those mountains are really what causes something called a thermal inversion. And a thermal inversion, an inversion means something is backwards or it's been flipped. So typically, right, warm air rises through the atmosphere and that it's replaced by cooler air. You get horizontal winds that come in from the side to replace that warm air as it rises. What happens with a thermal inversion is that because you have mountains on either side of a city, or maybe a city is in a valley where it's surrounded by higher landscape around it, right? As that warm air rises, particularly if a cold front has moved in, that cold air is denser, and so it sinks down and it presses down on that rising warm air. And because of the shape of the land, that warm air can't escape. So it essentially sits on top of the city and acts like a cap, and it traps all of that smog in a layer underneath it. That's where you get this image right here. So this is colder mountain air up here. This is where all the warm air is that is rising out of the city off of the thermal mass of the concrete that's in the asphalt that's in a city, right? And it can't go anywhere generally until some kind of a storm comes in and kind of disrupts those layers of air and clears the air, right? You'll also get smog from things that are happening outside of cities. In several different places where I've lived, including here in Cambodia, you've got farmers who will burn the land in preparation for planting, and all of that smoke, that particulate matter, will drift into the cities and can contribute to smog, right? And smog not only has significant impacts on human health and the health of other organisms, it also has really significant economic costs. So this is a percentage of GDP. So here we are in East Asia and the Pacific, where 7.5% of the total GDP equivalent is lost due to urban air pollution. Right? In South Asia, India, Pakistan, Sri Lanka, Bangladesh, very similar, 7.5% almost. Right? Middle East, North Africa is significantly lower. Latin America and Caribbean also significantly lower. These are smaller land masses. Islands have good horizontal air movement because of their proximity to the oceans. Right? Economic losses. Here you go, 3 crops, wheat, rice, and maize in 3 different countries: China, Japan, and South Korea. Just in those 3 countries, ground level ozone causes about $63 billion in crop losses every year. Right? Those are direct crop losses from those crops being impacted by the ozone in the air. Right? Remember back in topic 1, I think it was 1.5, humans and pollution, we introduced the 3 tiers of pollution management strategies. You're going to need to apply it to photochemical smog. Right? So let's take a look at a bunch of pollution management strategies for smog. Right? Here you go. Consume fewer fossil fuels. That means change human behavior, adopt different means of transportation. Public transit like these trains or buses, or hey, you can walk or you can cycle because these don't release carbon dioxide. Tier 2, you can regulate and reduce the amount of pollutants into the atmosphere. This is where carbon pricing or the cap and trade mechanisms come into play. This is a very, very rapidly expanding global business. Right? Governments are involved in buying and selling these carbon credits. They've been structured so that innovative businesses can reduce their emissions and sell the excess emissions to recoup some of the costs that they invested in that research and development. Right? Catalytic converters. These are devices that go into the exhaust system of vehicles, and they have this fine mesh of heavy metals in them that actually will trap a lot of the primary pollutants. And so it reduces the amount of the primary pollutants entering the atmosphere. It doesn't eliminate it, so it's not tier 1, but it reduces it, so it's tier 2. Right? We can regulate the fuel quality, right? So we're looking at the carbon content of different fuel sources, right? And use those to generate more or less electricity or to fuel vehicles if we have specialized vehicles that run on like ethanol, something like that, right? And then tier 3, which is just cleaning up, right, is not necessarily inventing something that will extract the pollutants directly from the atmosphere, right? What we can do is we can sequester carbon dioxide. And one of the easiest ways to do that is simply to plant trees, right? Because those trees will, through the process of photosynthesis, take CO2 out of the atmosphere and build it into glucose that they then incorporate into the biomass of the tree, so that carbon stops being a greenhouse gas and becomes biomass and a form of energy for the ecosystem. Right? Currently, there are a lot of startup businesses that are trying to do carbon sequestration mechanically from the atmosphere, and they're able to do it, but so far nobody's been able to figure out how to actually turn a profit through that process. Right? So to recap, 3 tiers of pollution management strategies for photochemical smog: change your human behaviors, walk or cycle to work, use public transportation, increase the energy efficiency. Tier 2, capture or regulate the emissions, cap and trade, tax the pollutions, install catalytic converters, install scrubbers on industrial smokestacks, regulate the quality of the fuels. And then tier 3 is you clean up the environment predominantly through reforestation activities, or potentially kind of a technocentric approach of carbon sequestration through an industrial process. Welcome everyone to today's video about IB ESS topic 6.4, acid deposition. Today we're going to learn about acid deposition, which is a form of air pollution that affects soil, water, and living organisms. The first big idea you need to remember is that acid deposition, often called acid rain, even though it's not always rainfall, can impact living systems and our built environment. Acid deposition is mainly caused by the combustion of fossil fuels, such as coal, oil, and gas. When these fuels are burned, they release sulfur dioxide and oxides of nitrogen as primary pollutants. These gases can react with water vapor and other chemicals in the atmosphere to form secondary pollutants, such as sulfuric acid and nitric acid. These acids can then fall to the earth as dry deposition, such as ash and dry particles, or wet deposition. That's rain and snow. Acid deposition can have harmful effects on the environment depending on the acidity level and the sensitivity of the ecosystem. There can be both direct and indirect effects on living systems. Direct effects can directly damage aquatic organisms and coniferous forests by lowering the pH of water and soil. For example, fish eggs and larvae may not survive in acidic water, and the needles of coniferous trees may turn brown and fall off, as you see in this image here. That means that they are not photosynthesizing properly. Indirect toxic effects mean that acid deposition can indirectly harm living organisms by increasing the solubility of metals, such as aluminum ions, in water and soil. These metals can be toxic to fish and plants, especially in low pH conditions. For example, aluminum ions can damage the gills of fish and make it so that they have difficulty taking in oxygen. There are also indirect nutrient effects, in which acid deposition indirectly affects the growth and survival of plants by leaching away or taking away essential nutrients from the soil, such as calcium and magnesium. These nutrients are important for plant health and productivity, especially in acidic soils. Acid deposition isn't just a local problem. It's also a regional and a global one. The impacts of acid deposition may be limited to areas downwind of major industrial regions, but these areas may not be in the same state or even in the same country as the source of emissions. This map here shows the prevailing wind direction in the United States and the concentration of hydrogen ions in precipitation. You'll notice that the heaviest areas are in the northeastern United States, meaning that those pollutants have been carried from the southwest. Sulfur dioxide and oxides of nitrogen that are emitted from coal-burning power plants in China can travel all the way across the Pacific Ocean and cause acid rain in North America. To reduce the negative effects of acid deposition, we need to adopt pollution management strategies that involve altering human activity, regulating and monitoring the release of pollutants, and cleaning up and restoring damaged ecosystems. Some examples of these strategies are altering human activities. We can reduce our use of fossil fuels or use alternatives that produce less sulfur dioxide and oxides of nitrogen, such as natural gas, solar power, or wind power. We can also improve our energy efficiency and conservation by using public transportation, carpooling, or biking instead of driving. International agreements and national governments may work to reduce pollutant production by setting emission standards, imposing taxes or fines, or providing incentives or subsidies. We can regulate and monitor the release of pollutants by installing devices that remove sulfur dioxide and oxides of nitrogen from coal-burning power plants and cars before those pollutants enter the atmosphere. For example, scrubbers like this one can spray a mixture of water and limestone on flue gases to neutralize sulfur dioxide, and catalytic converters can convert oxides of nitrogen into nitrogen gas and water vapor. Catalytic converters you find on the bottom side of automobiles. They're made of some very valuable metals, and lately they've become the target of many thieves who resell the metals for profit. We can also try cleaning up and restoring damaged ecosystems as a tier 3 approach to pollution management. That means applying measures that counteract the effect of acid deposition in soils, water, and in living organisms. For example, spreading ground limestone in acidified lakes can raise the pH level and restore the balance of minerals. Recolonizing damaged systems with acid-tolerant species can also help restore biodiversity and ecosystem functions. To evaluate the effectiveness of these pollution management strategies, we need to consider various factors such as cost-benefit analyses, the stakeholder involvement, the available technology, political will, public awareness, and environmental ethics. We also need to monitor the changes in acid deposition levels over time using indicators such as pH measurements, precipitation chemistry analysis, soil nutrient status assessments, and biological diversity surveys, among other tools.